All right, I'm getting a lot of questions from the audience about what's going on with the TRAPPIST-1 planetary system. This is this incredible system that has a whole bunch of Earth-sized worlds orbiting around a M-dwarf, red dwarf star. Some of those planets are within the habitable zone, and we know that James Webb has done some observations of this planetary system, and we've already got some of the data back. And I think people are just waiting and wondering, when are we going to find out about whether or not there are atmospheres around some of these planets? And so today you are going to get the definitive, all-inclusive, complete explanation of what's going on, all of the research that has been done to try and figure out if there are atmospheres on the planets at the TRAPPIST-1 system. And so my guest today, your guide to the TRAPPIST-1 system, is Megan Gialluca. She is a PhD candidate at the University of Washington. She works in both astrobiology and astronomy. She's part of the Virtual Planet Laboratory. And Megan has been part of a lot of the research looking at the planets around the TRAPPIST-1 system and gives what is the most comprehensive analysis of what's going on with the planets. We go through the planets one by one, world by world, observation by observation, instrument by instrument. What can we be confident of? What are we unsure about? What does the future hold? If you want to know and really understand what is the scientific opinion of the TRAPPIST-1 system right now today, this video will keep you very satisfied. So enjoy this incredible conversation with Megan Gialluca. Megan, I have to first start with an uncomfortable question, and I apologize in advance, but this is the one that my audience is demanding of me, and so I have to pass it along to you, which is, what is the current state of the search for atmospheres at the planets around the TRAPPIST-1 system?
I mean, I think that's a fantastic question. That's really what my work is into. So if you don't mind me going on a little tangent, the TRAPPIST-1 system, as far as JWST is concerned, is really one of the most observationally favorable systems for Earth-sized planets in their stars' habitable zones, which we can also talk about what the habitable zone is later on if you'd like. And so what's nice about TRAPPIST-1 is that it's what we call a late type M star, which means it's one of the smallest and coldest stars that are on what's called the main sequence. And because of that, the contrast between TRAPPIST-1 and its planets is really nice. It's very favorable. We can see it through the JWST. The JWST is actually pretty limited to planets like these because, say, traditional sun-like stars with Earth-like companions, those are not observable with JWST at this time. And so that's why TRAPPIST-1, I guess to start, has been such a focused on system in the community. And so observations with JWST for TRAPPIST-1 started in its very first cycle, what we call GTO, or guaranteed time observations for JWST. Now, guaranteed time observations are separate from what we call GO, or general observer programs. The GO programs are typically what scientists apply to, whereas the GTO programs, and a lot of times, have to do with things that, say, people who work on JWST have already decided or want to look at. And so TRAPPIST-1 was there from, day one for JWST. But the first observation that was really published was an observation of the most interior planet, so the planet closest to the sun, called TRAPPIST-1b. And that was done by Thomas Green, as well as some other people from the community in March of 2023. And so what they did was used JWST's MIRI, or mid-infrared instrument, to look at one wavelength specifically during what we call secondary eclipse. So secondary eclipse is when the planet is about to pass behind the star. What's nice about that is we see the light from the star bounce off the planet's atmosphere and then come to the telescope. And so this is very sensitive to either reflected light, or in the case of the March 2023 observation, what we call thermal emission. So the other thing you can see when the planet passes behind the star is what that planet is actually emitting. Planets like Earth tend to emit in the infrared. And so as it passes behind the star, you get the star plus the planet's emitted light. And then when it's fully blocked by the star, you get just the starlight. That means you can subtract the starlight out and see what the planet is emitting. And so that's why it's very sensitive to the planetary temperature, which defines in what wavelength the planet emits at. And so Green et al. Measured what we call the 15 micron photometric bandpass for the most interior planet, TRAPPIST-1b. Now, 15 microns, all molecules, all gases in an atmosphere are going to prefer to absorb or emit at different wavelengths. What's really special about 15 microns is it's a massive, massive carbon dioxide feature. Carbon dioxide is extremely sensitive, so it produces very large features. And so what's nice about this bandpass is it's a very easy way to say, well, does this planet have any CO2 in its atmosphere whatsoever? Since TRAPPIST-1b is so close to its star and it's so hot, one of the theories at that time was, well, maybe it's like Venus in our solar system, which has an atmosphere that is almost entirely composed of carbon dioxide. And so Green et al. 2023 looked at TRAPPIST-1b's emission, and what they found at 15 microns was that its equilibrium temperature, its brightness temperature, was 503 Kelvin. And I'm spitting out a number, and I'm sure that doesn't mean much to you now. But what's important about that is if you were to do, say, a theoretical model, super simple one, of a planet at TRAPPIST-1b's distance from TRAPPIST-1, and you were to say this planet is going to have no atmosphere whatsoever, so it can't redistribute heat, and let's make it even worse, let's say it has a zero albedo, meaning it's absorbing all of the incoming light, its dayside temperature would be 508 Kelvin. And so the fact that they measured 503 Kelvin matches that exactly well within 1 sigma. And so to us, at first glance, that's like, oh no, that planet probably doesn't have an atmosphere. Because what an atmosphere would do, it'd be served to redistribute that energy around the planet. And that would allow that dayside temperature to be much less than what it would be if there was no atmosphere present. And so that measurement came out, and that kind of rocked the community a little bit, because we really thought, there's probably some CO2 there because it's so potentially Venus-like. At the same time, it wasn't too surprising because of the star that TRAPPIST-1 is. And this gets into my research a little bit, so I'll leave it off here for now. But the basic idea is TRAPPIST-1's very active. And so it puts out a lot of stellar wind, which can strip atmospheres. So once we got that TRAPPIST-1b measurement, that's pretty much what everybody points to. Like, well, star is so active, it's stripping the atmosphere of TRAPPIST-1b. If there is any atmosphere present, it's probably very, very small on the nanobar level or less. For reference, Earth's atmosphere is 1 bar. A nanobar would be like 10 to the negative 9 times our atmospheric pressure. But overall, it really seemed like that wasn't the case. And so shortly after that, in July of 2023, I can't pronounce his first name, but E et al. 2023, he's advised by Eliza Kempton over at the University of Maryland, I believe. They expanded on the atmospheric modeling associated with the green observation. So they were looking at, okay, is there anything we can get to match to this? Bare rock compositions, atmospheres, etc. What they found, well, they confirmed that CO2, so any atmosphere containing at least 100 parts per million of CO2, that would be like a mixing ratio of 10 to the 6, so any atmosphere containing that much CO2 that's greater than or equal to 0.3 bars would be ruled out to greater than 3 sigma confidence. So if I'm not sure if anybody's familiar with how we report confidences in science, I'm sure they are, but as a reminder, 3 sigma is pretty confident, 5 sigma is very confident. Anything within 1 sigma, we would say matches. Anything within 2 sigma is very ambiguous. So then what they also reported in E2023 was that atmospheres with gases that do not strongly absorb in this region could also match still to TRAPPIST-1b. So I just want to remind you, we only have one data point at one wavelength. So any gas that doesn't affect that wavelength, we're completely unsensitive to. However, with that one data point, right, and what we know about atmospheres theoretically, it seems very theoretically implausible that you would have an atmosphere that has no strong absorbers in that infrared region that would bring the continuum down at all. So that is why they ended up concluding that the most likely case is that it's a bare rock. with surfaces including potentially basaltic, metal-rich, or iron oxidized. So that's what really matched after the green observation. And then again, shortly after that, in September of 2023, so we're really talking about month-long timescales here, Olivia Lim published a paper who's advised by Bjorn Benneke and some others from the TRAPPIST-1 community. They used NIRIS, which is another instrument on JWST, to observe 2 visits, so 2 transit observations of TRAPPIST-1b. So we talked about emission observations, and transit observations are when the planet passes in front of the star. And so what you're looking at in that case is the light coming from the star, passing through the atmosphere and coming to your telescope. Now, there's a big problem with transmission observations right now with TRAPPIST-1, and I'm sure you know what this is already. I'm sure a lot of your viewers do as well. It's stellar contamination. Turning out to be a huge problem. I'll leave that for the next question because there's a whole lot to talk about there. But just for now, just understand that these transmission observations, we're in trouble with them. They're not very sensitive at this point, and we're working on how to disentangle the planetary signal still. There's a lot of good stuff being done there, though, so we should definitely talk about that. But in this particular case of TRAPPIST-1b, what they found was the first visit had star spots with almost 30% coverage. The second visit had faculae with also almost 30% coverage. And so it was less sensitive than the green observation for ruling out a lot of atmospheric compositions. Essentially, what they were able to conclude was that a clear, low mean molecular weight atmosphere, such as a clear hydrogen-dominated atmosphere, would be ruled out to very high confidence. This didn't surprise anybody, I think, in the community. Past work on TRAPPIST-1 had already basically ruled out hydrogen-dominated atmospheres, but this work was extremely important to understanding the stellar contamination that we're going to be facing. So then finally on TRAPPIST-1b, the last part of our story that's publicly available comes from Elsa Ducrot, and that was published actually in December of 2024, so last month. Elsa Ducrot, also with, again, a lot of others from the community, including somebody named Michael Guillon and also Thomas Green himself, the guy that took the 15 micron. They published 5 visits at 12.8 microns. So the same thing, secondary eclipse emission, so probing temperature, but they looked at a different wavelength, so a different bandpass that would be sensitive to different molecules. And what they found at 12.8 was that when they considered, let's say, both the 12.8 and all of the 15 micron observations, they reported a brightness temperature of about 420 Kelvin at 12.8 and 478 Kelvin at 15. And so the 478 at 15, that matched the green observations. So that's still like, okay, probably bare rock. But the 424 at 12.8 microns actually didn't match the green observations reported temperature at about 2.1 sigma. So it's still very ambiguous, but it's not within 1 sigma. So it's not certain is what that means. And so that kind of threw a wrench in things, because up until then, everybody's like, it's a bare rock, it's a bare rock, we're certain it's a bare rock. And then we get the 12.8 observation, we're like, well, this is a little funky. And for reference, what that measurement showed is basically a dip that you would maybe not expect in that planet's, let's say, line of temperature versus wavelength. And that can sometimes indicate that an atmosphere is present. The tricky thing, though, is trying to interpret what that is. And so what I will say is that the most likely explanation is still that it's a bare rock. And when you consider the 12.8 and the 15 micron together, it's most consistent with a fresh ultramafic surface, which is exciting in and of itself. And I'll get back to that in a second. But I want to talk about the atmospheric interpretation for a minute. So when you have the 12.8, let's say, in a case, let's say, where we would expect a CO2 atmosphere to be, you would have the 12.8 at a high temperature, and then the 15 micron would dip way down to a low temperature. The reason for this is because CO2 is absorbing here, you're actually seeing the light from much higher in the atmosphere. And if you want me to continue to elaborate on that, I get it. This can be a tricky kind of thing to wrap your head around. At the 12.8, where CO2 doesn't absorb in an atmosphere like that, you would see deeper into the atmosphere, closer to the surface, and so you would report the temperature as being higher. And that's because in an atmosphere like Venus, the temperature increases with pressure. So the closer you get to the surface, the hotter it gets. However, that doesn't necessarily have to be the rule of the universe. So you could say if the surface was cooler than the top of the atmosphere, you would have an inverted structure where you would have the 12.8 being a lower temperature. And then as you probe higher in the atmosphere, you would see a higher temperature. And so what that means is that an atmosphere could match to TRAPPIST-1b if there was what we call a temperature inversion. So that's what that means, is that instead of temperature increasing with pressure, it decreases with pressure.
So, worst case scenario, it's a bare rock. Or most likely scenario, this is the one that people are converging on. Yeah. But best case scenario, based on that kind of atmospheric profile that you're talking about, what would that sort of look like? What kind of planet atmosphere would that be?
Yeah. So just a quick note, I don't want to use best case and worst case scenarios.
Sure.
I think either way, it's fantastic. We learn something about terrestrial planets. And it's good not to have a horse in the race, right? I just want to know what is true, not necessarily what I want. And so what that would mean for the atmosphere, for example, an atmosphere like that in the solar system is Titan. Now, Titan has a temperature inversion that would create a feature like that. However, it's not at those wavelengths because Titan has hydrocarbon hazes, which are driven by methane photochemistry in its atmosphere. A CO2 atmosphere, here's where the wrench gets thrown into things, is that we don't typically see CO2 atmospheres with a temperature inversion. Temperature inversions, as a general idea, can be caused by hazes, because hazes will cool the atmosphere underneath them while heating up the atmosphere above them, in some cases. However, Venus, which has a CO2-dominated atmosphere as well as photochemical hazes, does not have a temperature inversion. So from what we know about how planetary atmospheres work, and the bandpasses in which we have data, which would, if it was a temperature inversion, suggest it was a CO2 atmosphere, we don't have a very strong idea of how that would be theoretically self-consistently possible at this time. People are working on it. I'm sure they're working on it tirelessly. I know my own colleagues are working on it in some cases, but it's just uncertain right now, which is why theoretically the bare rock composition is still the best matching interpretation.
Right. So let's move on to C, because that was B.
That was B. So that's pretty much everything we have on B at this point. But what I will say is that there is a lot of unpublished data and data that's upcoming. For example, in cycle 3, which is being taken, this year as we speak, I was a co-investigator on an accepted JWST proposal led by Elsa Ducra to get more data at the 12.8 micron bandpass. So we're going to try and confirm that anomalous temperature is correct even, and see how it works over time. So there's data coming down the pipeline. Now, TRAPPIST-1c was kind of happening at pretty much the same time as B in a lot of cases, offset a little bit. So the first observation of TRAPPIST-1c came out in June of 2023, which was 3 months or so after the observation by Thomas Green of TRAPPIST-1b. And the first one of TRAPPIST-1c was taken by Sebastian Ziba. He's a graduate student at the time who's advised by Laura Kreidberg. And on this work actually included several folks from the University of Washington, including my PhD advisor and several of my collaborators and other advisors that I work with. And they did the same bandpass. So they started with the 15 micron in emission. You're going to see that a lot, by the way, with rocky terrestrial planets. That overall is the community's recommendation as the very first thing you should start with, because that bandpass is so sensitive to CO2. So they took 4 secondary eclipse observations at the 15 micron bandpass, and they found a brightness temperature of 380 Kelvin. So of course, taking the temperature by itself, you're like, what does that mean? I don't know. But if you were to do the theoretical model of TRAPPIST-1c in the same way as B, and you were to calculate what its temperature should be if the planet had no atmosphere, no heat redistribution, and was absorbing all incoming light, you would find to expect that dayside temperature to be 430 Kelvin. So 380 was observed, 430 if there is no atmosphere. And that means that their observed temperature disagreed with the expected airless temperature at about 1.7 sigma. So that is between 1 and 2 sigma, which means could be still airless, but also it doesn't match super well. So we're not really sure at this point in time. And so what they reported was that it would match within 1 sigma to NeO2, thin O2 atmosphere. We're talking about 0.1 bar with up to 100 parts per million of carbon dioxide. Or it could match to a 1 bar O2 atmosphere with 1 part per million of carbon dioxide, or pretty much any O2 atmosphere that has no CO2, let's say. So all of a sudden, some of these atmospheric interpretations that are very theoretically possible for TRAPPIST-1c are matching the data very well. And again, at this point, like, caution, that's one data point. You never want to draw conclusions off of one data point. But I would say, like, folks in the community, including myself, are starting to get a little excited. We're like, oh, this gives us some wiggle room to model atmospheres. They also found, I will say, that bare rock surfaces could fit within 1 sigma if they were fresh and basalt, so low albedo. That means they're reflecting some of that light away, allowing the surface to cool. Or if they were a weathered ultramafic surface. So some bare rock compositions are also fitting within 1 sigma. Basically what that means is we have no idea. The thing that we can rule out, right, is that it's a very thick carbon dioxide atmosphere. Because if that were the case, it would be even lower than 380 Kelvin. So then in September of 2023, which is, 2 or 3 months after that observation is published, Andrew Lankowski, who is actually one of my doctoral committee advisors, published work on expanding the atmospheric modeling for that 15 micron observation. This is very similar. Again, you'll see very similar parallels to how the community worked through analysis of the TRAPPIST-1b observation, which was followed up by the E2023 paper doing atmospheric modeling. The C observation is now followed up by another paper doing atmospheric modeling. And so what Andrew Lankowski reported was that they actually favored, as far as atmospheres are concerned, the thin oxygen, so 0.1 bar maybe, with up to 100 parts per million of carbon dioxide. And that fit very closely to the data, well within 1 sigma. And then they also found, which was kind of surprising, that pure steam atmospheres of really any pressure up to 3 bar would fit with the same agreement as the airless dayside temperature case, which was about 1.7 sigma. It's not a perfect agreement, but interesting nonetheless. Can't be ruled out because it's not at 3 sigma. And so that's kind of where TRAPPIST-1c started. And a lot of the work that I did in the past was on TRAPPIST-1c modeling, and a lot of the work that I'm actually currently doing is on TRAPPIST-1c, and so we can talk about that later on too. And then the last piece of the puzzle for TRAPPIST-1c was in January of 2025, which is this month. This was just published, although it was posted on the archive a few months ago. Michael Radica, along with some others from the community, like Carolyn Piola, Bjorn Beneke, and Nicholas Cohen, etc., he published nearest observations for 2 transits TRAPPIST-1c. So again, parallels between B and C, right? This was done for B by Olivia Lim. Now it's done for C by Michael Radica. Also, apologize if I mispronounce anybody's names and then they watch this video later. Don't get mad at me. So he used nearest observations of C, and they found, kind of the same thing as Olivia did, which is that stellar contamination is extremely prevalent. With TRAPPIST-1, they found significant signatures of spots and faculae, in both observations. But what was nice was that they actually matched observation to observation. The best fitting stellar contamination parameters did. So it looked like it was a pretty similar kind of amount of contamination, which makes it easier for adding those two observations together, let's say. And so, again, they confirmed the ZEBA 2023 conclusion by ruling out very thick atmospheres, but they pretty much agreed with their conclusion that it could be thin 0.1 bar O2 or less than 0.1 bar or bare rock compositions. And what was notable, though, about that study was that they were able to rule out greater than 1 bar steam atmospheres to greater than 2 sigma confidence. So that was something that was brought up by Andrew Lankowski's work, like, hey, this could maybe fit. And Mike Ordika said, yeah, it's probably not that, but we agree still with the best fitting interpretations, which is a potentially thin O2 atmosphere or bare rock compositions. So everybody's kind of in agreement, right? And so that is currently what's public for TRAPPIST-1c, but I will say phase curve measurements have been taken for B and C together at 15 microns again, which sounds like, why are you continue doing the same wavelength? This is actually different data. We could talk about what that is. That should be published very soon, early this year. And then the other thing is that we will be getting 12.8 micron data on TRAPPIST-1c with the upcoming proposal in cycle 3 that I told you about, led by Elsa Ducrot. And I think what's interesting, like if you look at the little breadcrumb trail, you can look at the public proposal PDF file for that. And what they do mention is that they got a partial data at 12.8 for TRAPPIST-1c and a like to be, it seemed unexpected. So that's pretty much all we know publicly about that. And so more data is coming down the pipeline.
And just to sort of repeat the question that I had with TRAPPIST-1b again, so like, you know, if TRAPPIST-1b is something like Titan, but made of different gases, but has this temperature inversion, what would be a sort of an interesting example that could explain the observations of TRAPPIST-1c, like a super Mars?
Like from an atmosphere standpoint. So what I will say is that, again, with TRAPPIST-1b, that's like if we had to fit an atmosphere to it, that's what it could look like. It could have a temperature inversion. We really have no standing at this point for saying that that is theoretically like making sense. So I would still go with the interpretation that TRAPPIST-1b is a bare rock. However, TRAPPIST-1c has a little bit more of a theoretical standing. And so this is where my work is actually into currently. And we can expand on what that is in a little bit if you want. But the best fitting atmosphere to TRAPPIST-1c at this point is a 0.1 bar O2 dominated atmosphere that's dry with maybe 1% of water or with a very low amount of CO2. So maybe 1 part per million or maybe 10 part per million, but very low, needs to be mostly O2 and needs to be very thin. That is actually a very theoretically possible atmosphere for TRAPPIST-1c. And the reason for this is that, and this is actually my last paper that I published last year, the star is going to be driving water loss on those planets when the system is first formed. And so any water, like let's say TRAPPIST-1 is formed, right? And you have volatiles on these baby planets. Volatiles, by the way, is any species like water that is gaseous at, say, room temperature, so it can evaporate. And so these planets form, they have water on them. Any water that's on the surface, because of the star and how M stars, like say, work for now, we can get into why that is. Any water on the surface is probably going to be turned into steam. So these planets are formed. Now they have at least a partially steam atmosphere if they had any water to start with that was on the surface. And they quickly move into what we call runaway greenhouse regimes. And so this is what we think happened on Venus. I would wager that most people have heard this phrase at some point in their life, maybe during like a high school physical science course. Almost certainly if you're taking a science course like this at an undergraduate institution. And so the runaway greenhouse regime basically just means that the planet is in this positive feedback loop where there's steam in the atmosphere, right? And steam will heat the surface, which causes more steam, which causes the surface to heat, which causes more steam. And it just keeps moving like that until all of your water is in the atmosphere and it's in steam and the planet is super, super hot. This is a really good way to lose all of your water because as it gets hotter, that steam moves higher and higher in the atmosphere. And once it's very high in the atmosphere, high energy radiation, I'm talking X-ray, ultraviolet radiation from the star, is going to come in and it's going to break those water molecules apart into its constituent atoms, so hydrogen and oxygen. Hydrogen is the lightest element in the universe, and it has no problem flying right off the top of the atmosphere. And so once you lose your hydrogen, you lose your ability to form H2O. So through that process, you're effectively permanently losing your water. There are some ways to get hydrogen on the planet, like impacting events, but it's very small in a lot of cases. It can be improbable. Most likely, when a planet after formation has lost its hydrogen, it's very difficult to get hydrogen back. And so TRAPPIST-1c, for example, has all of this steam from early in its history being what we call photolyzed. That's that splitting apart process. And then the hydrogen is escaping. It's escaping so fast that we call it hydrodynamic escape instead of traditional, what we call thermal atmospheric escape, which is Jeans escape. And so all of that is to say that it's losing it very, very quickly and very aggressively. And so in one very plausible evolutionary scenario, TRAPPIST-1c has completely dried out its surface. So there you get that dry atmosphere from. And when you lose that hydrogen, you still have O that was left over from the water that's now in your atmosphere. And O is much heavier. Oxygen is much heavier. It's about 16 times the mass of hydrogen. Hopefully you remember that, right? And the hydrogen is leaving so aggressively that it can actually drag a lot of that oxygen away with it and basically just a hydrodynamic flow. So it's just pulling things off of the atmosphere with it. It's ripping stuff off of the atmosphere, but almost certainly it's not leaving as quickly as hydrogen is. And so some of that O is being left behind and it's building up. And so in this very plausible evolutionary scenario, you can get a thin O2 atmosphere left behind while the water has ripped off a lot of the bulk of the oxygen. So it's very thin. And you're left with potentially a 0.1 bar O2 atmosphere. And then the carbon definitely makes things a little bit trickier because you would think this process, let's say, happened on Venus, right? And this is still actually an active area of research. Some people refer to it as the missing oxygen problem on Venus. How, if this process happened on Venus, did we end up with an atmosphere that's carbon dioxide dominated instead of O2 dominated? And the idea kind of gets at, well, you know, if you wave your hand a little bit and you say the O2 is weathered into the surface, it's like rust is how you might see that on Earth. Then that O2 gets into the mantle, geochemistry happens, eventually volcanoes are going to start spitting out carbon dioxide. That doesn't necessarily have to be the case, though. And so that's why we say on TRAPPIST-1c, well, there is the evolutionary pathway where it becomes a Venus. So it becomes carbon dioxide dominated. But we've ruled that out because the 15 micron observation doesn't agree with that. So now there's this other evolutionary pathway where atmospheric escape has stripped the planet of most of its atmosphere and all of its water, and it's left behind a very thin layer of O2. And how we can somewhat get around the idea that, well, why doesn't that turn into carbon dioxide is, as this process is happening, this atmospheric escape process, there's a lot of oxygen kind of hanging out in there, much more than 0.1 bar. And some of that, like I said, is being ripped away by the hydrogen, but other parts of it can actually go into weathering the surface. And so if there's a solid surface, it can weather that. But what's potentially more likely in that case is there's a magma ocean. And that removes oxygen a lot more efficiently than, say, a crust like the Earth. And what can happen is you can completely fill up, let's say, those oxygen buckets. So if your planet has this much room for oxygen, it can fill that up. And then it has trouble pulling more oxygen down into the surface. So that's potentially one way that you could end up with an atmosphere that currently fits the data that we have for TRAPPIST-1c. So that's something that we're absolutely looking at. We're absolutely testing. A lot of people are of the mind that you would have more carbon dioxide than we see in the data. And so I think there's a lot of people that feel the most likely scenario is bare rock. And I think that's totally fair. And then there's a lot of people like myself and like my collaborators who think, well, we really can't tell the difference between the two with the current data that we have. And so we're going to say that they're both kind of equally likely at this point. And so my current work, and I won't go too much into it until you ask that question, but my current work is basically theoretical modeling of very thin atmospheres to see if they are theoretically possible with a self-consistent photochemistry in climate model.
So we've got to talk about D next. And, this is one where I don't know of any papers that have produced any reports whatsoever on what's been found at TRAPPIST-1D, although the observations have certainly been made. I've watched them come and go in the schedule for JWST. What can you talk about the state of our understanding of TRAPPIST-1D?
Yeah,
and this is the first one that's in the habitable zone, and this is why this is quite exciting.
So TRAPPIST-1D is maybe in the habitable zone. It depends on what you use as your definition of the habitable zone. So maybe now's a good time actually to talk about what that is. So the habitable zone, I think, is a very useful concept that sometimes gets misused by people that maybe just hear the phrase habitable zone. It's not necessarily the area where planets are habitable. It's just the area where the distance from the star is just right that if you had, you could have liquid water on the surface, basically. So another good phrase for that is the light on water zone, which was coined by someone in the community that I'm missing their name at this point. We like to call it the light on water zone because that's really what it is. And so the interior habitable zone, let's talk about that for a second. Once you get interior to the habitable zone, the definition, right, is that no matter what you add into the atmosphere to cool the surface off, all of the water on the surface will go into a runaway state. That's what we were just talking about with the interior planets. So that defines the interior habitable zone. The outer limit of the habitable zone basically says, okay, once you go past this point, no matter how many greenhouse gases you add to your atmosphere to try and warm it up, all of the water is going to be ice. And so that gives us the habitable zone. And there is different ways to define the habitable zone. There's the traditional or the conservative habitable zone, and then we have the optimistic habitable zone, and then we have the empirical habitable zone, which is also sometimes referred to as the I'm going to mix this up, but the late Venus and early Mars, or the early Venus and late Mars, either way, they're defined by when Venus and Mars could have last been habitable. And those tend to be pretty optimistic. And so D falls in this, let's say, liminal region between where you could define the interior edge of the habitable zone. That actually makes it a very exciting planet because it can be a test of our definition of the habitable zone. If we look at D, right, and it's dry, arid, like B and C, or it looks like Venus, then we say, look, interior edge of the habitable zone must be further out. But if we look at D and it's, potentially habitable, then we say, it's over here, actually. So it's going to help us to define where those limits actually lie. However, there's other challenges with D. Mainly, it's a very small planet, so it has very low surface gravity. For reference, TRAPPIST-1b and C are both about Earth-sized and slightly bigger. So TRAPPIST-1c, for example, has a mass of 1.09 times Earth's mass. TRAPPIST-1b is a fraction of Earth's mass. It has very low surface gravity, and so it's much easier to lose your atmosphere in the same process that we talked about for TRAPPIST-1c, for example. It's even easier for that hydrogen and oxygen to leave. And so because of that, I think it's tempting for many people to say, well, let's just focus on C and E, because E is very squarely within what we think the habitable zone should be for TRAPPIST-1. And then they kind of skip over D. And I think that's really reflected in the observations that have been accepted. Yeah, there have been some observations accepted for D, but nowhere near the level of observation time that's been given to B and C, or even E, F, and G. And at this time, to the best of my knowledge, there's nothing public for TRAPPIST-1D. However, there's been a lot of theoretical modeling cases for TRAPPIST-1D. For example, in 2023, my PhD advisor, Dr. Victoria Meadows, published a paper that was essentially looking at D and E in particular. And what they found was it's actually very difficult to sustain a habitable atmosphere on TRAPPIST-1D. But while that is to say, we really need the observational test. And so I think it's very important to not forget about D, because it can be very key to our understanding.
Okay, well, let's move to E then.
Sure. So TRAPPIST-1E, and as a matter of fact, we can just kind of talk about TRAPPIST-1E, F, G, and H, because none of them has very public data at this point. There's a little bit for F and G in terms of stellar contamination, but E, F, G, and H are still kind of on, let's say, the down low. I've seen some results published at conferences, but to respect the peer review process and the publication process, I'm going to refrain from talking about what I've seen there. What I will say is upcoming for E is very exciting. In cycle 3, there were 2 TRAPPIST proposals accepted in cycle 3. And one of them was a very large proposal done by Natalie Allen for 15 transits of TRAPPIST-1E, which is a lot. It's fantastic. It's really great. The trade-off there is that it's actually going to be split between cycle 3 and cycle 4. And so there's going to be, I don't think I have the exact timing, but, half or less of them was happening this year. And then half or greater than half is happening in cycle 4, so next year. And I do know that some of those observations have already been taken. And what's exciting about that, though, is that in all of the modeling work, that I've seen come out of my research group, from my doctoral advisor, that is enough transits and for us to be able to start to, let's say, fit some atmospheric compositions, provided we can appropriately remove the stellar contamination, which we feel very confidently that we are able to do because of the way that we've set up these observations. So we can start to talk about the stellar contamination if you're ready for that. And that is actually where the observations of F and G were published. But really, there's no atmospheric interpretations from those observations at this time that I have for you, just what we saw stellar contamination-wise.
Okay. So yeah, I mean, this is the big confounding element that I think has cropped up in the last couple of years, is that it turns out these red dwarf stars are, really hard to distinguish from their planets. There's a lot of this, as you say, this contamination of the signal coming from the star itself. When did the community start to recognize the scale of the contamination and how tricky this was going to be?
Yeah. So what's interesting, that I think was, let's say, brushed under the rug, is that the community was aware that this was going to be a problem. I just think that it was a much bigger problem than we had initially thought it would be. And so this actually starts in January of 2018. So that's 3 years before JWST was launched. 2 or 3 years. I'm not going to do the math right now. But before I get into that, I just want to talk about the physics, right, of why the stellar contamination is happening, what on the star is causing that, because I think it's easy to wave our hands and say, stellar contamination, but I want everybody to really understand what's causing that. And it has to do with features on the surface of the star, let's say. So you might think about the sun. We know that the sun has all of these different types of activity. It has sunspots. It has what's called faculae, which is maybe a little less known. It has flares. It has coronal mass ejections. And I'm guessing, again, from even high school science, a lot of people have heard of what these are and they're familiar with it. All of these things can happen on other stars too. And so in particular, the things that are giving us the most trouble are the sunspot or the star spots. They're not sunspots anymore, the star spots, and the stellar faculae. So as a review for everybody, sunspots, oh my God, I'm going to do this a million times. Star spots are spots on the star that are much cooler than the surrounding region by a few thousand degrees Celsius. And those, again, all of this is active areas of research, but the kind of general thought process works. This is a good enough understanding for me to do my job, so it's good enough for you guys too. Is that local magnetic activity on the star is strong enough to redirect the energy, the heat from the interior of the star that's being convected up towards the photosphere, which is kind of like the stellar surface. And so it redirects that energy. It creates a local cool spot, and that is a star spot or a sunspot. Because these sunspots are indicative that weird stuff is happening with the stellar magnetic field, we associate these sunspots with lots of other activity, like flares. And flares happen when magnetic reconnection occurs. So we have all these field lines, they're all tangled up. I just think about it like strings tied in a bunch of knots. And then all of a sudden, they get pulled tight into how you would expect a magnetic field to look. And when that reconnection happens, it accelerates electrons towards those field lines to the photosphere, and that causes stellar flares. And stellar flares are basically enhancements of the radiation coming out, where they peak mostly in the near UV wavelengths and also in the blue visible wavelengths. And so that's star spots and also flares. And then faculae are kind of, I just think about them as the opposite to spots. So they're local bright areas on the star where the temperature is much higher than the surrounding region. And those are also caused by local magnetic activity. They're actually also often associated with star spot cycles, which makes sense, right? I guess the way I like to think about it, don't know if this is strictly accurate, but I think, magnetic fields push energy away, you get a sunspot, and all that energy has to go somewhere else, and you might get a faculae. That's kind of like the way it feels nice in my brain. And so the issue when it comes to stellar contamination, right, is we're looking in transmission at the planet passing in front of the star. And so it would be nice if we could see a star and it would look like the sun and we see the whole surface. I don't know if you've seen the SOHO and SDO images, but they're gorgeous. That would be fantastic. Unfortunately for us, TRAPPIST-1 is a little dot of light. And the planet passes in front of it and we see a dip in the brightness, and that's about it. And so we have no idea if that planet is passing in front of sunspots, if it's passing in front of faculae, or if, more importantly, there are sunspots or faculae on other regions of the star where the planet is not passing in front of. And the reason why that is so important, we call them unocculted star spots or faculae, is because when we're thinking about the transmission spectrum, we have to remove the stellar light. And so we look at the star before the planet passes in front of it, and we say, okay, this is our baseline. And then we would imagine, okay, now the planet's passing in front of it, and if I know what the baseline is, and I know how large the planet is, I should know exactly how much light is supposed to be removed by an airless rock. But I don't, because I actually think that, what actually happens, right, is if the planet passes in front of the star, but there's star spots over here, then the planet's going to be blocking out more light than you'd expect. And that's a problem because we want the atmosphere to block out more light than we would expect. And so when we have these unocculted star spots and unocculted faculae, it's messing up that signal of the light we're receiving as a function of wavelength. And to make matters even more complicated, the star is rotating. So sometimes those spots and faculae will rotate into view or rotate out of view in the observation, which messes up the brightness curve even more. This isn't a problem for these emission observations because you're always seeing the entire star the entire time. That's why we like them, because they're very robust against the stellar contamination. And then the other issue is flares. Flares can just wash out your observation entirely, or just create peaks in the brightness that are much greater than the atmospheric signal that you're looking for. So that is why stellar contamination is such a problem. With M-type stars, it gets even worse because these stars are what we call very active. So they have a lot of star spots, of faculae, and of flares. And so it makes it even harder for us to observe those types of stars in comparison to something like the sun, which is, in comparison, relatively quiet. And so the TRAPPIST-1b observations taken by Olivia Lim in 2023 with NIRISS, those are transmission. Those were the big headline that kind of came out at the time. It was very public, that stellar contamination is a problem. They found signs of unocculted star spots in their first visit, and they found signs of unocculted faculae in the second visit. And so everybody's like, well, here we go. Transmission is going to be very tough. It hurt us a little bit with the TAC, that's the the time allocation committee, people who decide who gets time on JWST, because they saw that and they were like, no more transmission observations for TRAPPIST-1 until you guys figure out what's going on there. That's a little bit reductive. They're very smart people, and there's a lot of science to do in all different fields. So totally understand. But that's what happened with the stellar contamination. And so what we knew going into this was that this type of contamination would happen, the process that I just described to you. We call it the transit light source effect, or the TLSE. And this was, there's a lot of papers on it. I will say one of my favorite papers on it was done by Ben Rackham in January of 2018. I have the dates written down. That's why it took me a minute. So Ben Rackham in January of 2018 really published a paper on this for TRAPPIST-1 and what he might expect. And his predictions are actually pretty spot on. He predicted 8 plus 20 minus 10% spot coverage for TRAPPIST-1, which kind of matches up with what Michael Radica saw, which was 29% spot coverage. And then he predicted 54 plus 16 minus 46% faculae coverage, which also had a coverage of about 29%. And they warned that contamination may be on the order of 1 to 15 times the strength of atmospheric features, which is very spot on. They're washing out the features, right? And so I think what was surprising was just how prevalent it was in our observations. And in terms of stellar flares, Ward Howard and his collaborators published a paper in December of 2023. And that's where the TRAPPIST-1 F and G observations come into play. And they looked at the nearest observations for 2 transits of B, 1 transit of C, 1 transit of F, and 2 transits of G. The 2 transits of G were taken with the near spec instrument, not nearest. The other ones were done on nearest. And what they observed was that there was 1 flare observed in the second transit of B, 1 flare observed in the only observation of F, and 2 flares were just prior to the second transit of TRAPPIST-1G. And so they looked at these flares. They did a lot of work. They inferred that they were present from the enhancement of H-alpha emission. So that is a feature, let's say, in that spectrum that we were talking about, that's just at about 0.6 microns, 0.65 microns, which is right within the observing region of those instruments. And it indicates that you have a lot more emission from hydrogen atoms. And of course, stars are mostly made of hydrogen. And so that can clue you in that a flare has just occurred. And so with these observations, as well as reviewing some observations done by Spitzer of TRAPPIST-1 in the past, they were able to infer that TRAPPIST-1 had a flaring rate of about 3.6 flares per day, which is a lot. Yes, so that is a lot of flares. That is 10 times higher than the predictions of TRAPPIST-1 from the K2 mission. And so that, I think, it illustrates how, we can be kind of caught off guard by how much stellar contamination there is. And so I like the way that this was put by Julien de Wit in, I believe it was 2024, in one of the papers he led for the community. This means you have about a 30% chance of significantly biasing your out-of-transit baseline for a standard 6-hour observation. And so anytime we observe a transit, it's around 6 hours of time we have to invest in, because we have to look at the star before the planet transits, and then during the transit, and then after the transit. And so whenever the planet is not in front of the star, that's the out-of-transit baseline. And so you're worried about flares happening during that time, which throw off what you think your reference light is. So that came out. What was exciting, though, about their work is they also worked on flare contamination removal. And in a lot of cases, they were able to remove up to 80% of the contamination. And so that is good. And that kind of illustrates that, it's okay. we can still use data if there's flares in it. Still give us the data, please. I think the trickier thing has been the unocculted star spots in faculae. What's very exciting. Yeah.
I was going to say, I mean, when you think about, say, the sun, and you look at, say, the surface of the sun, and you know, even during very active times of the sun, there are a few sunspots, and they are covering up what, like 1% of the sun's surface at the most. When you think about these sunspots that are blocking, what you say, like upwards of 30% of the surface of the star that you're seeing. Again, you know, it may be a big week, and NASA announces one M-class flare and above. That's exciting. But you're seeing multiple flares going off every single day, not to mention that huge amount of coverage of all the faculae. I don't know, that's like trying to study a monster.
Yeah.
That is just there, just freaking out in front of you, and then trying to puzzle out the planets that are going around it. And so it's no surprise that it's a really tricky kind of turbulent environment to try to capture any kind of data about the planets themselves.
Oh yeah. That's like the problem that we're facing. It's very, very difficult. And so you have, you know, this is what we call the M dwarf opportunity. This is kind of a general, I actually love these. I think people get so creative with the names for things. So before JWST launched, we realized we could study Earth-sized planets around the latest M-type stars. We called that the M dwarf opportunity. This is the opportunity to study Earth-sized planets before we could really look at, let's say, Earth twins. And we also have the K dwarf advantage. That comes into play for HWO. We talk about that later. But anyways, that's why, the M dwarf opportunity is so exciting, because we're like, well, we can finally do some of the science. Then everybody's like, oh, it's going to be tricky, though, because M dwarfs are drastically different stars. For the reasons that you pointed out, in addition to just our difficulties with observing them, you also have to remember that the habitable zone, because these stars are so cool, habitable zone is much closer to them. And you're right within flaring distance, right? And if the flares are happening more frequently, that's something that can also drive that atmospheric escape that we were talking about. And so going into this, right, we're really, nobody can know for sure, because this is the first time we're getting data, that M dwarf stars are even favorable to hosting habitable planets or life. That's something we're actively trying to figure out. But I'll be honest with you, I don't think we'll have an answer to that, even in the duration of JWST's mission, because it's such a complicated problem. And as you've seen, we're working with 1 or 2 or 3 data points at a time. And so,
and the TRAPPIST-1 planets are the best. They're the best of the best.
The best to observe.
And yeah, with JWST. And so once you've fully characterized the TRAPPIST-1 system as best you can and have to move on to other planetary systems, then the quality of the data is only going to go down.
Yeah. I would say it's not even necessarily the quality, but it is the time you have to invest to get the same quality of observations, right? So like if I look at a planet that's outside of TRAPPIST-1, instead of investing, a couple days of observing time, I might have to invest a week of observing time. And so we get less time to do that. So we have to pick our targets more carefully, or we get less data overall. It becomes more difficult. And there have been, I will say, other observations of planets like TRAPPIST-1. In particular, like because of this emission thing, and it's nice and robust against stellar contamination, easy to do for the most part. We have looked at some other rocky planets that are expected to be well interior to the habitable zone where it's really hot. But yeah, like as you point out, TRAPPIST-1 is really the most observationally favorable system for your JWST. And as it turns out, there's not a lot of observationally favorable systems that have so many Earth-like planets or Earth-sized planets, let's say, around them at this time. And I don't want to do an injustice to anybody who's also studying terrestrial planets with JWST right now. There is a lot of really phenomenal work being done. And also with sub-Neptunes and super Earths. There's a lot of super interesting stuff going on with that field right now, too. So I did just want to add that caveat in. But yeah, overall, with the stellar contamination, it's very difficult for us to observe, but there is a light at the end of the tunnel. So we have an idea of what we're going to do. This original method of, let's say, stellar correction, to the best of my knowledge, was really put forward by Ben Rackham and Julien de Wit in, let's say, July of 2024 in a paper that they published. And in that paper, they really argued towards using higher fidelity models of stellar heterogeneities. Heterogeneities, for the record, is referring to those sunspots and faculae. So hetero meaning different and homo meaning straight. So homogeneous would mean the star looks the same across its face. Heterogeneities just means we have a lot of stuff that doesn't look the same, like spots, like faculae. And so they were arguing we need to observe stars more. A lot of people in the community like to say, know thy star, know thy planet. So we want to just observe the stars. That's a lot of observing investment. Another method that they put forward, which is what we're kind of going with right now, is to use the fact that TRAPPIST-1b is most likely airless. And so what they want to do is anytime you want to observe a transit of one of the other planets in the system, we want to observe it right before or right after a transit of TRAPPIST-1b. And all of these planets are orbiting their star on the period of days. And so that's pretty feasible to do. And the reason why we want to do this is if you have TRAPPIST-1b pass in front of the star, and you take it as an assumption that it has no atmosphere, that means any difference, any bumps, any wiggles in its brightness curve have to be due to the heterogeneities on the star. So you look at TRAPPIST-1b, you say, okay, that's what the stars look like. Here's what the star is doing. And then your other planet passes in front of the star, and you're able to subtract that stellar contamination that you saw with the airless planet. And so it's actually a very, very clever method, in my opinion, of trying to remove the stellar contamination. And what's really cool is that Alex Rathke, I might be pronouncing his name wrong, so I'm sorry if I did. He just posted, also with Julien de Wit and Ben Rackham and some other folks, onto the archive in December of 2024. So it's in the peer review process right now. The first paper that's demonstrating doing this for TRAPPIST-1b and C. So they demonstrated this novel method to remove the stellar contamination using one transit of TRAPPIST-1b, followed closely by a transit of TRAPPIST-1c with near spec. And they were able to find a 2.5 times reduction in the stellar contamination at those short or high energy wavelengths. The longer wavelengths, lower energy wavelengths, were a little bit harder to assess because they have lower SNR just off the bat. That's signal to noise ratio, by the way. So they have like higher, let's say, error bars on them. But if you took more than one observation, which we almost never do anyways, we always want to take multiple observations, then you can get that SNR to be lower, and they basically conclude the stellar contamination would also be similarly able to be removed. So that was really exciting. That was a super great result to see from them. We're all super excited about it. And that's going to make it so much easier for us to use these transmission observations and potentially, get more data that is done in transmission, which is really good for those habitable zone and outer planets, which are a little bit too cold to be effectively looked at in a mission. And we actually see this method already going into play. So I mentioned Natalie Allen's proposal for 15 transits of TRAPPIST-1e. Those are all using this method. So they requested 15 transits that had close but not overlapping with timing with TRAPPIST-1b. So they're going to use TRAPPIST-1b to remove the stellar contamination, which is great because that means that their data is probably going to be quite good.
And if people are interested, I do have an interview with Julien de Wit here on the channel a couple of months back, sort of talking about that exact topic, which is why I was sort of a little more knowledgeable about the stellar contamination side of things, which is good. I'm sort of building my understanding one conversation at a time. What are you obsessed with right now?
I think it's pretty obvious. I'm obsessed with TRAPPIST-1. So obsessed with it. I feel so lucky that I get to be one of the people working on the TRAPPIST-1 observations because I think it's one of the most exciting areas of research science right now. It really just blows my mind, I think, that this is the first time, right, in human history that we're really able to try and study the atmospheres of Earth-sized planets in habitable zones of their host stars. And so that's always that always puts me in awe. And I think there's a lot of focus that gets put on life detection, and also on habitability detection, which is so great. And actually, I have a final note to say about that, but remind me after, which is so great, right? And I think those things are super important. I want to search for them. But I think what's also really exciting is just learning about how terrestrial planets evolve in general. Even if we don't have life on that planet, does it look the same as Earth or any of the planets in our solar system? Does it have volcanism? Is the volcanism the same? Are the surfaces made out of something different? So we're learning all of these things about science in general and about how it works in the universe that we've never gotten to see before. And I think that is just as exciting as the search for life. As a note on life detection, because I hear this a lot, which is like, when are we going to detect life? It's happening soon, right? And there's been, right, you've probably seen in the last even few years, there's been some kind of claims of biosignature detections and stuff like that. And, while you've given me this platform, right, to talk to people that care about my field and the work I do, I just wanted to tell a cautionary tale, I guess, about what the very near future is going to look like, especially when HWO comes online. I would not be surprised if we start seeing lots of claims of biosignature pop up more and more frequently. And I think the more that happens, the more disillusioned people are going to get, because we'll have a biosignature claim and we won't be sure. We might not ever be sure if it's a true biosignature. And I don't want people to get discouraged because we haven't discovered life, or because we have biosignature claims and then it turns out to not be life. I think that's going to happen a lot. And I actually think that being able to tell definitively if we have discovered life is maybe even well past HWO. We might need more missions after HWO to really determine that. And so I think that as far as life detection in the universe goes, we're going to end up in this era of uncertainty, potentially. And I think that's really exciting. And it's the first step to life detection. But I want people to temper their expectations for that and to not get swept up in sensationalism when a biosignature claim comes out. Always ask questions, always wonder if it could be a false positive. And the community is doing a lot of work to try and come up with standards of evidence, for example. And how are we going to communicate when we think we could have found something that's life without, giving people the wrong impression, which is also super important.
Yeah, and I 100% agree with you. And that's definitely my personal stance. I mean, I think I've gone from somebody who's been like, oh, if you see oxygen, that tells you there's life, right? To like, I'll give you an example. I'm working on a story right now that astronomers have detected dimethyl sulfide forming in interstellar clouds near the core of the Milky Way. And this had been considered a really interesting potential biosignature that can only potentially be formed by the presence of life. And here we go. Once again, the universe is showing that it can form these really complex molecules all by itself, just in clouds of gas. And so, and the other example that I always give is, like, you look at Venus and you look at the controversy about the detection of phosphine in the atmosphere of Venus. Venus is right there. Like we
right
can
there.
go and we can sniff its atmosphere with upcoming spacecraft, and yet there is this controversy. And when you compare how accessible Venus is to planets that are tens of light years, hundreds of light years away from us, it is tricky work. And we're going to live in this inconclusive land until, we have the 10-meter telescope out at the solar gravitational lens that is seeing aliens walking down the street reading their newspapers. That's when we finally get those conclusive answers. And until then, we're going to have to enjoy the ambiguity, enjoy the search, enjoy the mystery, follow the process, and not get too disappointed and hyped up about what happens. So don't worry. This channel has your back, but I know that it's going to be a tricky time for science communication.
Yeah, absolutely. And so I really appreciate that. We're completely in agreement, and we're working with 1 or 2 or 3 data points, where, as you pointed out, there's a lot of places in the solar system where we have lots more data and we're still not certain. And scientists are doing their best. They're just people, and we're all trying our best to communicate honestly and effectively. And I think that it is a good time to get excited, but obviously let's not get so excited that we give up when it doesn't turn out to be life after all.
It's like, have fun and enjoy the mystery while it lasts.
Yeah.
Yeah. Well, Megan, thank you so much for taking the time to chat with you. Thank you for that comprehensive, gold standard explanation of what's happening with the TRAPPIST-1 system. I had no expectation that was going to happen, and I'm so happy that that's what you came really armed with the information, and that was wonderful. Thank you so much.
Yeah, my pleasure. Thanks for having me. This was super fun.
I hope you enjoyed that conversation with Megan Gialluca. Now, Megan, in addition to working on the TRAPPIST-1 system, is starting to think about what kind of work needs to be done with the Habitable Worlds Observatory. This is, of course, this next generation that comes after James Webb that should be able to actually characterize, directly observe Earth-sized worlds orbiting around sun-like stars. And one of the problems that we saw with James Webb was that micrometeorites could impact the mirror and cause problems with the observations. What impact will that have, pardon the pun, on any work done with the Habitable Worlds Observatory? We talk about that, but also just like what it's going to take to be able to do more direct imaging of exoplanets, try to find that other Earth-sized world orbiting around a sun-like star. Now, we've got that additional conversation over on my Patreon. It's available free, so you can just go and follow us for free, and then you can get access to that additional interview. Now, I'm going to talk about some of my thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Barry Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Robach, Sean Sargent, Spiderswap.io, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So I think that conversation right at the very end of the interview really touched upon something that I am becoming more and more aware of as I sort of dip my toes into what the scientists are working on. And that is the ambiguity, the uncertainty, the fact that the question that we want to answer, are we alone in the universe, is going to be a very difficult one to actually find a definitive proof. Like, obviously, if the aliens show up and they hover above our cities, or if we see trees on Mars, then we'll know that we're not alone in the universe. But probably the evidence is going to be very hard to gather. It's going to take us a long time, and the case will build over long periods of time. And it might not happen in our lifetimes. Well, maybe not my lifetime. I'm old. But for many of you watching, we may not find out a definitive answer to the question, are we alone in the universe? But that doesn't mean we shouldn't search. It doesn't mean that we shouldn't keep working, pushing away, chipping away further and further out into the cosmos, being able to understand just the true nature of the universe that surrounds us, and not what we hope is true, but what is really true. And it's only by doing this slow and steady work over potentially generations of astronomers will we get to some semblance of an answer and a true insight into the true nature of reality. So, I'm enjoying the journey so far, and I hope you are too. All right, we'll see you next time.